All right, section 4, solving polynomials in factored form. Okay, this is going to be kind of the introduction of two, not new concepts, but at least two new things within this unit. First off, we're going to deal with solving, which means literally we're going to be getting solutions where it's like x equals this value, y equals this value, whatever that value may be. Okay, so in the previous sections leading up to this, it's pretty much been standalone polynomials, combinations of like terms, doing the multiplication stuff. It's never like x equals this number or anything like that. Now we're going to start getting into that with solving. We're going to talk about how that relates to polynomials in this section. The next thing we're going to be introducing here is factoring. Okay, this back half of chapter 2 is going to deal with this this topic of factoring. In the overall chapter 2 title, it's called Polynomial Equations and Factoring. The factoring is what we're going to focus on now. Okay, so today's notes are kind of going to break up into kind of two different kinds of topics that are related to each other. But first thing I'm going to talk about is factoring. Like, what is factoring? How is factoring performed? You've actually done this in previous math classes in other ways, shapes, and forms. You may be familiar with greatest common factor, GCF. It's essentially built off the same concept. We're just going to be doing it with both numbers and variables. But I'll talk about that to start, mostly just to kind of refamiliarizing ourselves with what is factoring, how to do it. And then I'm going to talk about this guy, zero product property. This is going to be the reason why factoring is going to be so valuable for us. And just as a disclosure right now, this section, a lot of this unit in general, is more foundational for future higher level mathematics. So a lot of the things that we're going to be asked to do in this section, in this unit, may not really make sense in like the big, like in the small picture sense of things. But once you get into like math 3 and the higher level mathematics, this stuff will be referenced quite a bit. Factoring, zero product property, and why it's useful. Okay, we're really only going to be scratching the surface of this stuff, just kind of getting you familiarized with how to perform the math operations and how to rearrange things. Okay, so the kind of the payoff of doing these assignments won't be as great as it would in higher level mathematics. It'd be like, oh, that's why it's used in the real world. A lot of this stuff is kind of that transitional foundational stuff that will make that stuff possible in later classes. But for now, let's jump into what you will actually be seeing. So first off, factoring. What is factoring? What is the second half of chapter 2 going to be about? Okay, there is a formal definition of what factoring is, but it basically boils down to this. Factoring is the inverse operation of distribution. Okay, every math operation can be done and undone, basically. Okay, that's what an inverse operation does. It undoes something. Okay, and we've dealt with that already with like addition and subtraction, multiplication, division. Those are inverses of each other. It undoes one or the other. The same thing can be applied to distribution. And distribution is what we've done in the past couple sections. In the past couple sections, you were given problems like this: x times x plus 2, or 3y times 1 plus 4x. Okay, you were given some object or a polynomial multiplied by a polynomial. This is something that you've been doing for a while now. Distribution. You would take that object and multiply it throughout the parentheses. And what we introduced in section 2 and 3 was that if this front object happens to be another polynomial, it's the same multiplication and distribution. It's just that I have more objects to do that with. Okay? So this is what we started with in sections 2 and 3. Okay? Some form of being asked to distribute something and turn it into these polynomial sentences. Okay? And both of these results will have binomial results. Okay? So how does that undone? All right? Basically, we started with these parentheses, these multiplication problems, and performed the operation, distributed and collected like terms so that we get these polynomial results. But what happens if I start with the polynomial and want to work backwards to this form? This is what we would call a factored form. Okay, and that's going to involve the inverse property of distribution being factoring. Basically, if I'm able to distribute this x into this x plus 2 to get this result, I should be able to undo it and pull that x back out to get back to this factored form. Okay, so that's what factoring does. It essentially looks for greatest common factors. Okay, so in this section, what you're going to be dealing with is starting with polynomial sentences and being asked to factor it back to these parenthetical multiplication problem types of forms. So how is that done? Okay, it's basically going to be a lot of finding common factors. Okay, so in this case, in both cases, I'll kind of talk about both at once. All right, my suggestion will be similar to a piece of advice I gave you in section 2. Kind of split this up, compartmentalize it into dealing with numbers and letters separately. Okay, deal with the numbers first, move on to the letters next. Okay, so in this case, this first example here, technically there is a number, a coefficient multiplied by x squared. We don't write it because we don't need to, but it's technically 1, right? 1 times x squared plus 2x. So if I'm looking for the greatest common factor with my numbers between 1 and 2, well, 1 is the greatest common factor for the numbers, so technically I could pull out a 1 from each. Now, what do I mean by pull out a 1? If distribution involved multiplication and factoring is the inverse of distribution, I'm really doing the inverse of multiplication, which means I'm dividing. So what do I mean by pulling out a 1? That means I'm dividing out a 1. And really that does nothing. But when I divide x squared by 1, I get x squared again. When I divide 2x by 1, I get 2x. Okay? So that really didn't do anything special by pulling out the greatest common factor for my numbers. But this one will have a common factor with my numbers, 3 and 12. Okay? My greatest common factor between 3 and 12 is 3. Okay? In other words, 3 is divisible into both of these monomials. Okay, so if I were to pull 3 out of both of these monomials, I'm doing it by division. Okay, and so 3y divided by 3 would give me just y. 12yx divided by 3 would give me 4yx. Okay, now I end up pulling out 2 things at once because 3 is not the only common term here. But again, my suggestion is to first deal with your numbers, pull out the 3, okay? And now deal with my letters. Are there any letters in common? Well, both of these terms have a y. This one doesn't have an x, so that can't be a common factor because it's not common. But in this case, both terms have a y, which means I can pull that y out by division. Okay, so I would take this object here, this monomial, and divide y out. I would take this object here, divide y out. And basically, since both 3 and y were in common, 3y is my common factor, my greatest common factor in this polynomial. Okay. Up here in this one, 1 was the common factor for numbers. For letters, I have x squared, so technically 2 x's here, and just a single x. So my greatest common factor of my letters is a single x. It's the most things that are in common with the letters. So I would pull that out through division. X squared divided by x would give me just x. 2x divided by x would give me positive 2. And so x is the only, technically it was 1x, I just don't need to write the 1, but x was the common factor here. And so when I divide these objects out of the original polynomials, the parentheses is what's left over. So for instance here, the greatest common factor was just x, or 1x if you want. Okay, if I were to divide 1x or just x out of x squared, I'm left over with just x, a single x left over. If I were to divide a 1x or just x out of positive 2x, I get just positive 2. That's my factored form. And if I were to redistribute this and collect my like terms, I get right back here. Right? For this one, 3 was my common number, y was my common letter, so 3y is my common factor. And so when I divide 3y out of each of these monomials, here's why I keep emphasizing that division, because a lot of people think it's subtraction. And the reason why they think that is they're like, oh, if I pull 3y out of 3y, nothing's left over, and I just have 0. Well, that's not true. Because if I'm dividing 3y out, 3y divided by 3y is not 0, it's 1. So when I'm pulling things out, when I'm dividing things out, I'll never get to 0. Okay, there will always be something left over, even if that object is just 1. So again, dividing 3y out of 3y gives me 1. Dividing 3y out of 12yx, deal with your numbers and letters separately, right? 4 when I divide the 3 out, and then when I take the y out, y over y gets the y's to cancel, they go away, technically to 1, but then just the x will be left over, 4x. Okay, so both of those are an example of how to factor. You have done similar things in previous classes with pulling out greatest common factors and all, but just get prepared. You're going to be doing that quite a bit in this section. All right, so that's how to factor and what factoring does. But why is it useful? So here in the margin, I say, like, here is why it's going to be useful. Let me scroll up a bit. Zero product property. This is actually going to be a very basic concept, one that you are also going to be familiar with. But here is the formal definition. If a product of 2 or more quantities is 0, then at least one of those quantities has to equal 0. Basically, it breaks down like this. If I multiply a string of things together, whether I'm only multiplying 2 things or if I'm multiplying 100 things, if any one of those numbers is 0, the product, the result, has to also be 0. Let me phrase it this way. If I were to give you a multiplication problem like 8 times 5 times 3.76 times 17.436 times 8.5 times 175 times 0, it didn't matter what all those other numbers were, because anything times 0 has to equal 0. Those are the multiplication problems that you got in elementary school that you really always hoped for, because it was just a really quick answer, right? Anything times 0 is 0. Well, let's look at the flip side of that coin. If I have 2 numbers that are multiplied by each other, and it doesn't matter what these 2 numbers are, but if I have 2 unknowns, like in this case, a times b, that equals 0, the flip side of that coin says that the only way I can multiply 2 things or any number of things together to get 0 is if one of those things happens to be 0. One or more, I guess. So in this phrase, if a times b is 0, then either a has to equal 0 or b has to equal 0 or even both. But I have to, like, one of them has to be 0. The only 2 numbers I can multiply to make 0 is 0, and then the other number could be anything. But one of them has to be 0. I can't multiply any 2 other numbers together to get 0. That's impossible. Okay? So let's apply that to the previous 2 examples that we just did. Why would that matter? So here's kind of the new format that you're going to be seeing in this section. The stuff that's changed here is now I have an equal sign, and in most cases it's going to be set equal to 0. In some cases it won't. We'll talk about what to do in those cases. The spoiler alert is you're going to rearrange it so it's equal to 0. But this is what you're going to be kind of dealing with. And here's the significance of setting it equal to anything, let alone 0. As soon as I have an equal sign and make this an equation, that implies that I can now solve for x. Like, x has to be some specific set of values. And you'll see why I said values plural in a minute. Okay? But we're going to use this concept, the zero product property concept, to apply it to this. Now, as these are written, both of them as polynomials, polynomial sentences, okay, I can't actually get x by itself. I can't get y by itself. There's a simple reason why. Because these are both set up as addition, and they could have been subtraction, that didn't matter. But because they're written as they are with these operations of addition, I can never combine these terms. X squareds can't combine with x's. Y's can't combine with yx's, right? These are 2 different terms, so I can't combine them. And even if I were to try moving stuff away from one of the variables to get that variable by itself, I would always end up with another variable on the other side of the equation, which is a problem because then I can't solve for x. So here's how we can bypass that. We're going to use factoring. So we already talked through how to factor both of these. We went through that before. So here's the factored version here. X squared plus 2x being factored was x times x plus 2. That was this factoring that we just went through up here. Pulled out those common factors. It's still equal to 0, but now I have a factored problem. Here's why this is going to be more useful. This was addition. Can't combine those, can't smush them together in any way, shape, or form. Even if I were to get a variable by itself, I'd have a variable on the other side. Doesn't mean no good. But in this case, now I have multiplication happening right here. Why does that matter? Because now I can apply this concept. I have two objects being multiplied by each other. One of those objects happens to be a polynomial, x plus 2, but I have two objects here. X times x plus 2 equals 0. Based on this concept, if either x or x plus 2 equals 0, this will equal 0. So what am I going to do? And here's kind of the punchline of the entire section. If I have two objects multiplied by each other to make 0, set each object equal to 0 and solve. So my first object here is x. Well, if I set that equal to 0, I'm actually done. X equals 0, that one's solved for. Didn't even have to do any work there, just had to write it. So x equals 0. I'll talk about what that means in a second. Now my other object, x plus 2, this could also equal 0, so I'll set that equal to 0. X plus 2 equals 0. Okay, and what we've just done is we've created two equations. X, this first object right here, equal to 0, and x plus 2, this second object, equal to 0. What this means is that if this first object equals 0, it actually does not matter what this turns out to be, because 0 times anything is 0. Now, flip side of that, if x plus 2, this second object, if that equals 0, it didn't matter what that first one was, because anything times 0 is also 0. So what we've done is we've prepared for both scenarios. This one happens to be already solved for because I have x equals something. That's just x equals 0. That one's done. But here, I do need to move something. I need to move that 2. And here's where we go back to our middle school inverse operations. I would subtract 2 from both sides, and I would get x equals negative 2. So what does this mean? I have two separate values. Both are correct. Here's what I mean. So if I take this x equals 0, and I were to plug it back into this phrase, if x is 0, 0 times 0 plus 2, well, this happens to be 2, but it didn't matter because 0 times 2 is still 0. If I were to take that 0 and plug it back into its original polynomial, which is technically the same, but if I were to plug 0 in, 0 squared is 0, plus 0 times 2 is 0. 0 plus 0 is 0. That one checks out. That's a solution. But also, if I were to plug in negative 2, negative 2 plus 2 is 0. And it didn't matter that that would be negative 2 in that case. Negative 2 times 0 gives me 0. That checks out. But if I were to plug it back into my original polynomial, again, the same thing, just unfactored. But if I were to plug in negative 2 squared gives me positive 4. And then negative 2 times 2 gives me negative 4. Positive 4 plus a negative 4 gives me 0. Another possible solution. Again, there is a significance to why there's more than one solution, but suffice it to say for now that that's how I'm going to solve these problems. It is possible to have more than one solution. Okay. Again, there is a reason why, and I'm not going to get too deep into it right now because I feel like that would just overcomplicate things. But for right now, I'm going to have two solutions. And it has to do with the fact that I have two objects being multiplied right here equaling 0. So for instance, we're going to do an example in a little bit where there's more than two objects being multiplied to make 0. And so the number of solutions has to do with how many objects are being multiplied. Okay. So real briefly, this last one, when we factored it, we had 3y times 1 plus 4x equals 0. Again, your punchline, what you're going to be doing, I have two objects here being multiplied to make 0. I'm going to set each object equal to 0. So 3y equals 0. 1 plus 4x equals 0. And now I solve for the variable in each case. And each of these cases won't be overly complicated. It's just going to be inverse operations. So for instance here, to get y by itself, I would divide both sides by 3. 0 divided by 3 is still 0. So y equals 0. On this one, to get x by itself, I'd first move this positive 1 by subtraction. So I'd get 4x equals negative 1. And then I need to move the 4 by division. So I would get x equals negative 1 over 4, or negative 1/4. So I'd have y equals 0, x equals negative 1/4. If I were to plug either of these values back into either the original polynomial or into the factored polynomial, In either case, I would end up with 0 as a result. Both will check out as answers. Okay, so let me jump into the examples here, just briefly talking through them. All right, A and B will be super fast. I'm just going to briefly talk through these guys, how to solve them. Again, your punchline. These ones are pre-factored. And by factored, I mean like you have a parentheses involved. You have your multiplication involved. Okay, essentially what you're going to do is you're going to take each object and set it equal to 0. So for instance, here I have 2 objects. 2x equals 0. X minus 4 equals 0. Again, applying that 0 product property that we used before. Because if either 2x equals 0 or x minus 4 equals 0, then that will be a true statement that it equals 0. Part B, the only reason I add this one is because it's a slightly longer string of multiplication, but the same rule is going to apply. Here I have 3 objects, x plus 1, x minus 3, x minus 2. If any one of the 3 objects is 0, it doesn't matter what the other 2 are, because 0 times that combination will end up in 0. So each parentheses will be set equal to 0. X plus 1 equals 0, x minus 3 equals 0, x minus 2 equals 0, and in each case solve. And in each case, it'll just be a one-step problem, but you'll end up with 3 solutions for this guy. Where I'm going to focus most of my attention to close out the class will be this one, because it's not factored. So what do we do in this case, where I have 6n squared equals 15n? So I'll deal with this one for the most part. I'll just show you the results for A and B, but I'll talk through this guy. All right, so let me transfer back over to our solution sheet. This is also uploaded on the Google Classroom. Here's A and B. Again, in both cases, I'm just taking each object, setting each object equal to 0 and doing the inverse operations at that point. So 2x equals 0. I divide both sides by 2. 0 divided by 2 is still 0. So x equals 0 is one of my solutions. X minus 4 equals 0. Add 4 to both sides. X equals positive 4. There's my 2 solutions, done and done. I could plug either back in and I'll get a 0 result. For this one, I have 3 equations. X plus 1 equals 0. Subtract 1 from both sides. X equals negative 1. X minus 3 equals 0. Add 3 to both sides. X equals positive 3. X minus 2 equals 0. Add 2 to both sides, and I get x equals positive 2. 3 different solutions that if any one of these 3 gets plugged into that polynomial multiplication, the whole string will equal 0. All right, so now part C. This is, you'll get a handful of problems that are like this one. This one tends to be about as complicated as it gets, so let's just jump right in. You're going to get some problems that look like this, where they're not factored, and it'll be obvious because there's no parentheses, okay? So I have 6n squared equals 15n. So the other problem here is that it's not equal to 0, like these other 2 were. So I give you a nice 3-step process here for how to solve any of these, because ultimately it's going to come down to solving for, in this case, what does n equal? So my first step is to first make it look like my problems at the beginning of the notes, where it's equal to 0. So rearrange the equation to solve for 0. The way I do that in this case is that either 6n squared has to be moved over here to the right, or 15n has to be moved over to the left. It actually does not matter which one moves. So I'll just go ahead and move the 15n. Since it's a positive 15n, I will subtract it to both sides. Had it been negative, I would have added it. But in this case, it's positive, so I subtract 15n from both sides. Now I get 6n squared minus 15n equals 0. Okay, so I officially have it equal to 0. That will be important for me to use the 0 product property ultimately. But step 1, rearrange the equation to solve for 0. You want your stuff to equal 0. So if there's other stuff over here, move everything away from that one side so that you have everything on one side and 0 on the other. Step 1, rearrange the equation to solve for 0. Step 2, factor. This is what we did at the beginning of the notes. Because you'll notice this is unfactored. I have a subtraction between 2 monomials. There are no parentheses. This requires factoring, which means I'm looking for greatest common factors. And my suggestion here, separate your numbers from your letters. Focus on my numbers here first, 6 and negative 15. The greatest common factor between 6 and negative 15 is positive 3. If I were to divide 3 out from 6, I'd get 2. If I were to divide 3 out from negative 15, I would get negative 5. Okay, but they also have letters in common. So once I'm done looking for my common factors with my numbers, move on to my letters. I have n squared and n. They have an n in common. So when I pull out both 3 and n, I'll be doing that with division. That's how I do factoring. So when I divide 3n out of 6n squared, I'm going to be left over with positive 2n. There's my greatest common factor, 3n. So when I divide out of 6n squared, I get 2n. When I divide 3n out of negative 15n, I get negative 5. Okay, and so there is my factored form of that same polynomial. 3n times 2n minus 5 equals 0. Step 1, rearrange your equation to solve for 0. Step 2, factor so that now I can apply the zero product property because now I have a product being done right here. And now this is just like these previous problems. Okay, now that I have a factored form equal to 0, I can set each factor equal to 0. 3n equals 0. Divide both sides by 3 to get n equals 0. 2n minus 5 equals 0. A little more high maintenance, but I still can move the stuff away using my same inverse operations. I'd move the 5 with addition, add 5 to both sides. I get 2n equals 5. Now I need to move the 2 by division. Divide both sides by 2, and I get n equals 5 over 2. 5 halves, or 2.5. All right, I'm going to stop recording.